So we have three goals for this particular lesson. We're going to do some definitions. We're going to compare redox reactions to acid-base reactions so that we can kind of find some similarities between the two. And then finally, the last goal is probably the toughest one. We're going to assign oxidation numbers to elements in a reaction so that we can understand where electrons are going in an oxidation reduction reaction. So first off, a little comparison between acid-base chemistry and electrochemistry. With acid-base chemistry, we were concerned with transfer of protons or transfer of hydrogen ions, same thing as a proton. So we looked at equations that look quite like this. We had cyanic acid plus water, and what we were looking at is the acid is the proton donor, the base was the proton acceptor. With electrochemistry, we're going to be this time tracking where an electron goes. So you can see with the Cu2+, it becomes Cu with no charge. So we can see that it had to have accepted 2 negative electrons to undergo that change, whereas the electrons had to come from somewhere, and they're coming from the iron. So the Fe goes from Fe, and with no charge, to an Fe2+. So that's the electron donor. So we're going to be tracking those electrons as they're transferred throughout the system. Why we study electrochemistry is electrochemistry has to do with conversion of energy. We're looking at the conversion between electrical energy to chemical energy, or vice versa. And there are a lot of technologies, tons of applications with electrochemistry. We could be concerned with energy storage and conversion, for example. We might be concerned with corrosion. If you want to know why your bike has a rusty chain, well, you need to understand electrochemistry to explain why and how to prevent that. We can look at industrial electrolysis, looking at sensory equipment. And then as well, there's some organic electrosynthesis as well that is kind of new technology and that we're trying to harness as well, rather than relying on things like fossil fuels. So there's lots and lots of different types of electrochemistry and applications to do with this. And these are just some of the particular examples. So here is an example. If we have a reaction between copper and silver nitrate, this is one of my favorite examples to do with electrochemistry as well. Copper, when you put copper into a silver nitrate solution, first off, the silver nitrate solution looks just kind of gray, kind of grayish in the water. It's kind of like murky water. And you put in a copper, copper shiny stick or piece of metal into that reaction. What happens in that reaction is that the silver starts to displace the copper. The silver actually comes out of solution and starts to precipitate onto the copper piece of metal, whereas the copper is actually dissolving and starts to go into the water, and it makes the water look all blue because of the copper color. So it's kind of an interesting reaction. The balanced chemical equation that's taking place here is we have that solid copper going with that silver nitrate, and we have a single replacement reaction where the copper is switching places with the silver. We can also break this down into the total ionic equation, just like we did in the last couple of units. So in this one, we're going to break everything that's aqueous down into its ions, and the solid stays together. It's only a single solid. And then what we do for the net ionic equation is we cancel all of our spectators. And in this case, it's the nitrate ion that's the spectator. So what we end up here is with the copper, and we get those 2 electrons transferring to the silver. And in the net ionic equation, you can see how everything kind of sorts itself out after that. So another way of tracking these electrons is the oxidation number. You may have noticed that the charge changed between the copper and the solid and the ion, and between the silver and the ion. This is what we're doing with oxidation numbers. We're tracking those electrons and seeing what takes place here. And there is a rule system for tracking those electrons, trying to figure out what kind of charge and where the electron is going to. So the first rule is very simple. if you have an atom in its elemental form, it has an oxidation number of 0. So you can see I've got 3 examples here. Doesn't matter that I have a diatomic atom here with the O2, diatomic molecule, sorry. All atoms in their elemental form have an oxidation number of 0. So all of these are oxidation number of 0. There's rule number 1. Rule number 2 is if we have a charge on that particular atom, so if we have an ion, the oxidation number is equal to the ion's charge. So there we go for our ions. Rule number 3 gets a little bit trickier. The oxidation number of oxygen is -2, but we have 2 exceptions. So you can see that as long as we don't have a peroxide, something like H2O2 or Na2O2, or we have OF2, our oxidation number will be -2. If we have a peroxide, then the oxygen is a -1. And if we have oxygen difluoride, then the oxygen is +2. And that has to do with the electronegativity. Fluoride is more electronegative. It is better at attracting an electron than oxygen is, and that's why it takes on a negative charge. It's taking the electron away from the oxygen. Rule number 4 is that the oxygen number of hydrogen is +1 unless you have a metal hydride. So if you have a metal mixed with hydrogen, then the hydrogen is going to take on a -1 charge. And usually we write the hydrogen after the metal, so it's another kind of tip-off that you've got something weird going on. So here you can see with hydrochloric acid and with water, hydrogen has a +1 charge. With the calcium hydride and lithium hydride here, hydrogen takes on a -1 charge. Okay, getting up there, we've got another rule. Oxidation numbers in compounds must sum to 0. So you can see with magnesium oxide here, MgO, all of the oxidation numbers have to add up to 0 because it has no charge. So we know that oxygen is going to have a -2 charge. That means that magnesium is going to have a +2 charge. Same thing, next one down, we have sodium hydride. We know that the hydrogen is going to have a -1 charge because it's mixed with a metal. That means that the sodium has to have a +1 charge. And with this rule, we can go back and look at some of the other compounds that we looked at in rules 3 and 4 and figure out what the oxidation number is of those other elements in the solution. So going back here where we had the oxygen mixed with the sodium, so we had sodium oxide, we know if the oxygen is a -2 charge, there are 2 sodiums that are mixed with that, and it means that each sodium had to have a +1 charge so that it balances out and adds up to 0. So +1 plus +1 plus -2 is equal to 0. With calcium oxide, the oxygen is a -2, and that means that the calcium, because there's only one of them, has to be a +2. We can do the same thing with the peroxide here, only this time the hydrogen is going to have a positive charge. And with my oxygen difluoride, if the oxygen has a +2 charge, that means that the fluorine has to have a -1 charge because there's 2 of them. Going through number 4 as well, we've got hydrochloric acid. If hydrogen has a +1 charge, that means that the chlorine is going to have a -1 charge. Hydrogen has a +1 charge with the water. Oxygen is going to have that -2 charge. And calcium, +2, lithium, +1. Rule number 6, oxidation numbers in ions must sum to that ion's charge. So this time we've got ClO4 minus. We know that that whole compound, if we add them all together, it's going to equal -1. So I've got 4 oxygens and each of them have a -2 charge. So I'm going to do 4 times -2 gives me -8. I know that my chlorine minus the 8 is going to give me -1. So I can kind of solve for x here. Chlorine has to have a +7 charge, so that 7 minus 8 is equal to -1. In the next example here, we've got a little bit different. We've only got 3 of the oxygens, yet it's still giving a -1 charge. So this time I'm going to do 2 times 3, or -2 times 3 gives me my -6. And when I add that to the chlorine's charge, it's going to still give me -1. So in this particular example, chlorine is going to have a +5 charge. Okay, last rule. Last rule is about with common oxidation numbers. And you're probably looking at these right now going, something about this is familiar. Maybe you're not quite sure where I'm coming from. But when you look at these are the charges that we give those when we're doing the swap and drop, when we're putting compounds together. And you can think right back to grade 10 when we started looking at if we put lithium with oxygen, how many lithiums am I going to need? So these are my common oxidation numbers. Alkali metals, the ones that are on the far left-hand side of the periodic table, have a +1 charge. Alkaline earth metals have a +2 charge. That's the second column down. Halogens, which are on the far right-hand side, next to the noble gases, have a -1 charge. And the chalcogens, which are sometimes called the oxygen family, they're kind of 2 over from the right-hand side, all have a -2 charge. So with this one, you can see calcium chloride. We've got 2 common ones stuck there. The calcium is an alkaline earth metal. The chloride is a halogen. Magnesium nitride here, we've got magnesium being +2. Again, we can do a little bit of math here to figure out what the nitrogen is going to be. If we do +2 times 3, that's +6. The nitrogens, there's 2 of them, have to add up to 6 as well, or -6. So each of them is -3. Strontium is an alkaline earth metal as well, and the sulfide is a chalcogen as well, so we've got +2 and -2. And then finally, lithium bromide. Lithium is an alkali metal, and bromine is a halogen, so we've got +1 and -1. Now, if you're ever trying to figure out oxidation numbers and you kind of find that 2 rules are contradicting one another, usually it helps if you start with rule number 1, and as you get farther away from rule number 1, they're more apt to kind of break the rules a bit. So you can kind of go in order. Oh, and I lied. There's one more rule, sorry. Generally, the more electronegative element takes on a negative oxidation number. This is what I was talking about earlier with the more electronegative. You can see here that as you progress towards the right-hand side of the periodic table, specifically fluoride or fluorine, okay, it is the most electronegative element. Also, as you go up the periodic table, we get more electronegative as well. So we can use that to try and figure out how to track our electrons as well. And here's the example. If we have phosphorus pentafluoride here, the fluoride is going to take on the negative oxidation number because it's the most electronegative. So it's going to be the -1. When we go to balance out the charge, that gives my phosphorus a +5 charge. The next one here as well, you can see that nitrogen is the most electronegative of these ones. Sulfur, very close as well. They're both going to be negative. And then the carbon is going to end up taking on the +4 charge. So that -3 minus 2 is -5, plus 4 gives me that overall charge of -1. Here are some examples. I suggest right now that you pause the video, see if you can figure out the oxidation numbers for each atom in those species, and then unpause the video when you're ready for the answers. Okay, going through the answers here for the first ones, we're going to work through the rules. We figure out the oxidation number of oxygen first, hydrogen next, and then the silicon will come after. So I know I've got 2 hydrogens, so 2 times +1 charge. I've got 3 oxygens, so 3 times -2 charge, plus whatever the charge of the silicon is going to give me a final answer of 0. So 2 minus 6 plus x is 0. And I do a little bit of algebra. I can find out that the charge of silicon has to be +4. The next one, we can kind of go through the same progression. Oxygen is going to have a -2 charge. We've got 4 oxygens times -2 plus whatever the astatine is going to give us an overall charge of -3. So we solve for that x, and charge of astatine is +5. With the next one, what I'm actually going to do to make things a little bit easier is to actually break it down into the ions. So I know that lead nitrate, lead is going to have a +2 charge because there's 2 nitrates that are going with it. So immediately that's going to give me my charge of my lead. I'm going to look at oxygen next. It's going to have the -2 charge, and then finally I'm going to solve for the nitrogen. So 3 oxygens times a -2 charge plus whatever the nitrogen charge is going to give me that overall charge of -1. And that's just coming from the nitrate ion, so that NO3 minus. I could go back and do the math for the entire thing, but I've already separated it. I already know the charge of the nitrate, so it just makes it a little bit simpler. Okay, finally, D. If you did do the questions and you paused the video, perhaps D is giving you a little bit of a headache and you're trying to figure out what the heck's going on. With D, the first thing that we're going to do is identify that hydrogen has a +1 charge. That means that we've got 4 carbons, so 4 times X, plus my 10 +1s, and it overall has to equal 0. Well, when I do the math here, I find that when I solve for X, it gives me -5/2. And you know what? The charge of carbon is -5/2. We can actually have fractions, and it occurs quite frequently when we're looking at our hydrocarbons. It doesn't occur very frequently for anything else. So congratulate yourself if you got that one all by yourself. Here are some other problems for you to try if you had a little bit, found the other ones a little bit tricky. So again, pause the video, see if you can get these yourself, and then I'm just going to give you the answers for all of them all at once. Okay, here's the answers for all of these. If you had any problems with these ones, make sure you drop me a note, give me a call, and I can help walk you through them. Oxidation numbers are one of those topics that some students get right away and some really struggle with. So if you're struggling, you're not alone. Okay, the last thing that we're going to talk about here is some definitions, looking at what oxidation and reduction is. We often call these redox reactions, and redox stands for a reduction and an oxidation all taking place kind of at once. There are 2 mnemonics that you're going to want to use. You can pick which one you like best. One is called oil rig. The other one is Leo goes grr. And Mr. Boyd makes the best impression of Leo the lion going grr. Please ask him if you see him in person. So first off, when an atom loses electrons during a reaction, its oxidation number becomes more positive. So the way you can remember this is oxidation is loss of electrons. There's the oil, or you can remember this as the Leo. Loss of electrons is oxidation. So you can see down here at the bottom, there's a little diagram, and you can see the oxidation taking place where the oxidation is losing that electron. Similarly, we can look at the reduction. Reduction is gain of electrons, RIG, so there's the rig, or gain of electrons is reduction, GER, GER. So the one being reduced is gaining the electrons. So here's my silver nitrate and copper solution example that I was talking about earlier. So that's the actual little diagram there, what's going on. When we have the copper plus the silver ions from the solution, you can see that the silver is gaining those electrons and the copper is losing the electrons. So for the oxidation half reaction, oxidation is loss of electrons. So the first thing that we're going to look at is what is losing electrons. Is it the copper or is it the silver? So the copper is becoming more positive. So copper can only become more positive if it's lost those negative electrons. So that's the oxidation half reaction. We call it a half reaction. The reduction half of the reaction is the silver. So the silver is gaining electrons and it's becoming that solid silver. It kind of looks all crystalline around the copper wire. So we're having electrons transferred from the copper to the silver. As we had with acid and base chemistry, with electrochemistry, we also always have to have an oxidation paired with a reduction. Just like in acid-base chemistry, something always had to be receiving that proton as something else was donating it. So every reduction must be paired with an oxidation. Now, the one tricky part about this class is we have oxidizing and reducing agents. So another approach for analyzing these reactions is to look at the species that causes the other species to gain or lose the electrons. So if a species is oxidized, it causes the other species to be reduced. So we call that the reducing agent. So a species that's oxidized is the reducing agent. Species reduced causes the other species to be oxidized. It causes it to lose the electron. So species that are reduced are the oxidizing agents. So this is just a pictorial representation here. X is losing electrons, so it's the reducing agent. It's causing the other atom over there, the Y, to gain the electrons. So here's an example problem where you might need that definition. It says, indicate the oxidizing and reducing agent in each of the following reactions. So what we need to do first is figure out the oxidation numbers of everything in there. So magnesium has an oxidation number of 0 because it has no charge. Hydrochloric acid, well, the hydrogen is a positive 1, the chloride is a negative 1. And on the other side of things, the magnesium has a positive 2 charge. Chlorine still stays with that negative 1 charge, so it's not being oxidized or reduced, but the hydrogen now has a 0 charge. Because magnesium has lost electrons, it is oxidized, and therefore it is the reducing agent. It causes the hydrogen to be reduced. That means that hydrogen must be the oxidizing agent. So pause it, see if you can figure out B as well. Then I'll go through it. So with B here, our oxygen goes from a charge of 0 because it's elemental to -2 when it's mixed with water or with nitrogen dioxide as well. So it's the oxidizing agent because it's being reduced and it's gaining those electrons. It's becoming more negative. The nitrogen, on the other hand, is the reducing agent.